Hello class. Today we have a new chapter and also a shift in the curriculum where we are starting the discussion of rigid bodies, more particularly the 2D or the planar rigid body motion. So chapter 16 point or section 16.1 to section 16.3 discusses the different types of rigid body motions and the rotation about fixed axis and the planar translation. While the chapter 16 talks more about the kinematics, we'll follow up with the kinetics and energy methods in later chapters. Now, so in similar approach that we had for the a particle, we will follow the same procedures, studying first the kinematics of rigid body and then move to kinetics. Now the difference between particle and rigid body is that a rigid body does have a shape or dimension and a mass, while a particle is a point that has a mass. Application of rigid body is in the amusement parks where you have a ride, a bus which is moving always or it's connected to this two cantilever mechanism that's rotating, because both of them are having even space. It makes the rotation or make the bus always leveled horizontal, meaning that this bus is undergoing a circular motion. Another example is the gears and pulleys. They are mechanisms that rotate about a fixed axis, the popular machinery. Also, example can be found in different mechanism in mechanical mechanism. Now, what is rigid body motion? Well, we are concerned only with the planar motion as we discussed earlier. Most often when the mechanism cannot be described by a point, it is necessary to study the system or a mechanism in terms of rigid body motion, which can be described by translation and rotation. So there are three types of planar rigid body motion. We have a pure translation or rectilinear translation, where every point within a body is moving at the same or does have the same characteristic of the other points. For example, if we map the path of point A and B, we'll find that point A and B is always parallel with respect to each other, and that's because it's translating in the rectilinear motion. And or in a linear motion. Now, in similar fashion, the same 2 points could have also have the same distance, but this distance is kept through a curvilinear path. For example, this example here showing a translation along a curvilinear path. A pure rotation can be described when a body rotates about a fixed axis, and general plane motion is when you combine these three together, where you have a translation and rotation. Now, let's talk about the rotation about a fixed axis. Let's take this body, which is experiencing a rotation in a circular path where every point on this body is rotating at the same angular velocity. And angular velocity describes the rate of change of the angle with respect to time, and this is in radian per second. In a general motion or general plane motion, where you have a body that experiences both of them, we need to describe the axis of rotation and also a Cartesian coordinate system that shows how this body is translating. Let's take an example where we have all kind of motion. This mechanism, it consists of a piston that goes left and right because it's guided through this channel, so it's a rectilinear translation as a cylinder. Every points in it move left or right, so it's a rectilinear translation. While the pulley is fixed about a point, so it is undergoing also pure rotation, as well as this over here, this link is pure rotation. However, this link is undergoing curvilinear translation simply because these two ends, this end and that end, which describe the ends of this link, are spaced by a distance r, which both of them undergoing rotation, meaning at every minute or every second or moment when this move an angle theta, this will move also the same angle theta because both of them are r. This will make sure that this link doesn't rotate, but it's gonna be moving up or down, right? And along the curvilinear path without any rotation. So it's a translation, curvilinear translation. However, this link, because this point is rotating and this point is translating, so it does have a combined motion, which is general plane motion. Okay, section 16.2 describe the velocity and position and also acceleration of a rigid body undergoing motion, general motion. To understand the general motion of a rigid body, let's take 2 points on a rigid body, point A and B. Point A and B, their position from a fixed coordinate system O are described by position vector RB and position vector RA or sub A. So therefore, if I want to measure the position of B with respect to A, it's as if there is a person on A looking at B and say, okay, the position of B with respect to A. So therefore, there is a relation. This is a triangle, and we can describe the position of B, RB, as of a position of RA plus position of RB with respect to A, which completes this triangle. So head or tail head is equal to tail head here. Or you can say position of RB equal to position of RA plus this in the vector equation. Taking the derivative of this position or and assuming that this body is only undergoing translation, meaning RARB with respect to A is simply zero, meaning it doesn't rotate because they are both of them move on the same rate. Therefore, their velocities are equal. Another way of saying it, take a derivative of this equation, knowing that if this is undergoing a pure translation, the relative position is zero, or I'm sorry, relative velocity is zero because it's not moving, because it's translation, and therefore this will drop. And then you have VB equal to VA, and also the acceleration if you take the second derivative. Alright, now in the cases when the body undergoing pure rotation about a fixed axis, like this axis O, which is described by the right hand rule, where your thumb is pointing onto the direction of the vector of rotation, and the rest of your fingers are pointing in a counterclockwise, showing the positive rotation of this body, which is as indicated over here. Therefore, the angular velocity, which is the rate of change of the theta with respect to time, or the derivative of theta with respect to time, is measured in radar per second, and it's a counterclockwise positive. Similarly, the angular acceleration, which is the second derivative of omega, which is going to be equal d omega dt, and that's going to be radian per second square. And this is going to be described by alpha. So alpha, always we use it here to refer to the angular acceleration, and it's a positive counterclockwise. Now, if the angular acceleration is constant for a system that is undergoing rotation about a fixed axis, then we can use the equation of motion to relate the velocity to time and acceleration and position using these three equations that we derived already uh, for particles in chapter 12, with the difference that omega here is the angular velocity, while we refer to it in the chapter 12 as a velocity. So this is going to be your initial angular velocity, and that's going to be your angular acceleration constant. So the angular velocity at any time equal to the initial angular velocity plus the angular acceleration, which must be constant multiplied by the time elapsed, are computed at the omega. Similarly, the angle at any time, or at time t, equal to the initial angle plus the initial angular velocity multiplied by the time plus half the angular acceleration multiplied by time square, and as well as the third equation. So this is good to be used only when the body angular acceleration is constant. If it's not constant, then go back to the definition and we do the simple integration of both sides. So for example, if omega is a function of time, to get the relation between theta and omega, and you integrate both sides. And this is how we got the equation. Before we move into examples, there is a couple of discussion points we want to clarify. Is first the rigid body rotation computed for a point. What is the velocity of a point for a system or for a rigid body undergoing pure rotation? I think we have discussed this in multiple occasions, but here is to remind you. Now, let's take this example 2D. The velocity tangential, or the if we are mapping point P of this rigid body, which is rotating, let's say counterclockwise, then the velocity of P is simply tangent to the path, which is V here, which is tangent to the P. And the magnitude of this velocity is equal to the angular velocity multiplied by the distance. So the more distance you have, the more velocity for the same angular velocity. Alright, in a vector and for general problems, it is a cross product where the velocity can be computed by omega cross the position between this point to a point that is landing on the axis and perpendicular, or not necessarily perpendicular, just any point on this axis, which is going to be in magnitude the perpendicular distance multiplied by the angular velocity omega. In vector, velocity of a point equal to omega cross rp. Okay. Now for the acceleration of a point P, using the normal and tangential components, we can describe the acceleration of a point on a body that is rotating using the normal an and tangential. For that point, the tangential is simply equal to the angular acceleration multiplied by the position r, and the normal component equal to omega square multiplied by the r. These are magnets, so the direction here is going to be of tangential is going to be in the direction of the angular acceleration tangential, and the normal is always pointing toward the axis of rotation. Okay, together will give you the magnitude of the acceleration, which is square root of these two components. Now, how did we get that? Remember that tangential velocity was omega r, or omega cross r. So when you take the derivative of, let me go back here, of this, it's going to give you the acceleration, and that's going to be, if you take the chain rule, it's going to be omega or d omega over dt cross rp plus omega cross drp over dt. Right? That's when you distribute the derivative. The first component is going to give you the tangential, right? This portion, where the w over dt, or d omega over dt, is alpha. The second portion, which is omega cross dr over dt, is the rate of change in the position, which is equal to, we can show it's equal to the omega square or r, where omega here, remember, is equal to v over r, which also can be described by this component here by vp square over r, or the angular, or the velocity multiplied square divided over r. So to recap all of that, we can write the acceleration in vector form as a equal to alpha cross r minus omega square r. These are vector, and that is cross product. So alpha cross r minus omega square r, which is this is tangential, and that is normal. The magnitude is going to be an square plus at square. Alright, procedures to solve any problem. Establish the convention along the axis of rotation. Remember that omega is the rate of change of theta with respect to time, and alpha is the angular acceleration, the omega over dt. And you can also use the chain rule to relate between the alpha, theta, and omega. And this will give you the equation of motion. And for a constant, angular acceleration will be similar to what we discussed in previous slides. Now, remember that this operation is a cross product, and you can use the determinant method. And remember these two equations, this one over here and that equation for the velocity. So you can write them in the component I, j, and k. Okay, let's take an example. Well, we have here a motor that turns the gear A. So there's a motor attached to a gear A, and this motor rotates at a constant angular acceleration of 4.5 radian per second, starting from rest position. This gear is meshed with another gear B, and the gear B that is attached to a pulley that doesn't have any relative motion with B, but is attached to it or welded, and there is a cable or a cord wrapped around the pulley D that has a dimension of 125 millimeter, and the gear B has 225 millimeter, and gear A has 75 millimeter. You want to find the velocity of cylinder C and the distance it travels in 3 seconds. Alright, the procedure to solve this problem. So we want to find the velocity of C, which is attached to the pulley, after 3 seconds starting from rest position. Okay, so we need to know the equation of the velocity of point P, which is the same as the C. So if we know the velocity equation as a function of time, we'll be able to substitute the time 3 and find the velocity of C. Now what we're given is the angular acceleration, which is constant for A. Now the angular acceleration, since it's a constant, so therefore we can write the equation, the angular velocity equation of point A to be equal to omega at any point equal initial angular velocity, which is 0, plus the time multiplied by the angular acceleration of A. So it's going to be equal, omega A equal to 4.5 multiplied by the time. Okay, so that's for A. How about P? Or how about this gear, because everything is used to that? Well, there's a relationship we can figure out that the tangent acceleration of point P as seen from A is same as the tangent acceleration of point P as seen by gear B. Similarly, the angular velocity of, the velocity of P, which is tangent to A and B, gear A, are equal. So what we can say about that is omega A multiplied by the RA, which provide the velocity P, equal to the angular or the velocity of P from B, which is omega B multiplied by R P, seen by gear B. Okay, so this relationship will give us the relation between omega and omega B. Okay. Alright, so let's go over the procedure step by step. So gear A and B will have the same speed and tangential component of the acceleration at the point where they are meshed. Therefore, we can write A tangential from each side to be equal, and that will give us a relationship of alpha B equal 1.5, since alpha A is given. Okay, and assuming that the cord is attached to the poly D and does not slip, the velocity and acceleration of cylinder C will be the same as the velocity tangential component of acceleration along the poly D. Therefore, the acceleration of C is the same as saying alpha D multiplied by RD. And therefore, the alpha, since it's constant, we can write the equation of motion utilizing the velocity of C equal plus the initial 0 plus the angular acceleration of C, which is moving tangent at the tangential acceleration of 0.1875. That's gonna give you a velocity of C. In a similar fashion, you can write the equation of motion for C, which relates to the velocity of related to the acceleration C, computed after 3 seconds. Okay, let's take a concept quiz. A disk is rotating 4 rad per second, where point A is crossing axis X. If it is subjected to a constant angular acceleration, which is clockwise, 2 radian per second squared, determine the acceleration at B. We want an acceleration of B. Acceleration of B has two components. The first component is going to be tangent, and it's going to be going to the left, so it is in magnitude, it's equal to 2 multiplied by the distance. That's going to give you tangential acceleration. So it's a 2 by the radius of this circle is 2, so it's going to be 4, and going to the left, which is negative I. So it's a negative 4I. Okay. The second component is the normal, which is pointing from B going to the O, and that is in the J direction positive. And the magnitude is equal to R omega square. Omega square is 2, multiplied by 2 is 4, multiplied by 2 is going to be equal to, sorry, the omega is 4, so it's 4 by 4, 16. 16 by 2 is 32. So that's going to give you negative 32. So the answer is D. A frisbee is shown and curves to the right. It is experiencing, a frisbee is thrown and curves to the right. It's experiencing what kind of motion? Well, it's a general plane motion. Right. Now, the last exercise is a group problem solving. This problem is two gears meshed to each other, gear A and B, given that gear A is described by a time variant angular acceleration. And we want to calculate the angular velocity and angular displacement of gear B at time equal 2 seconds. So the solution is already shown in the PowerPoint presentation, which is attached on Canvas. Please go over it. It's required integration to go from, and also requires knowing the relationship between gear A and B through the tangent acceleration and tangent velocity. Alright, so with this we finish section 16.1, 2, and 3. I will post new problems for the past two lectures.